All right, everyone, welcome to another week. We are going to start this week off by discussing 12 volt and high voltage charging system technologies. Some of the objectives that we want to take a look at is to describe the construction of the 12 volt charging system and some of the components that are there. I also want to make sure that everyone has an understanding of how the charging system indicators and instrumentation actually work. And we want to talk about the construction of and operation of the hybrid charging systems, which are vastly different from our current structures. We're going to compare the operation of the 12 volt charging system as well with that of a hybrid. And then, of course, try to prepare you for ASE questions that you might encounter in the future. So we're going to start off by discussing the 12 volt charging system that currently exists in most vehicles. And let's go over some of the functions. So one of the first functions is that it recharges the battery. And it recharges the battery typically after we've used some of the energy to crank over the engine when the starter engages to get the engine running. That energy is used and we use the alternator to replace the energy that was used to charge it up. We can also use the alternator if we were listening to our radio for a period of time out in the vehicle. Or maybe we had the fan on or something while we're waiting for someone while we pick them up. We use up the energy in the battery, we need to replace it, and we use the alternator to do that. It also supplies all of the 12 volt electricity once the engine is running for all of the components on the vehicle. So it charges up the battery and then serves everything else. Additionally, it provides 13 to 15 volt output, slightly higher than what's normally found in a battery, which is 12.6 volts. So this changes current and voltage output to meet different needs of the vehicle. So if you've got more consumers on, such as the radio and the heater and the rear defroster, there's more electricity being used, the alternator adapts to that need and charges more. It also provides smooth DC voltage for proper function of the vehicle electronics. Our vehicles operate on 12 volts DC, but an alternator puts out AC voltage, which needs to be rectified into a DC voltage. The main components that make up the 12 volt charging system, the parts of this system, is first and foremost the alternator, which is an AC generator. We also have something called a voltage regulator, which actually is able to control those current fluctuations that we need. We have a drive belt that connects the alternator via a pulley system to the engine. Then we'll have a charge indicator of some sort in the vehicle to indicate if we're not charging. And then we'll have a charging system harness that connects all the components together, as well as a battery and then the engine ECM, which actually the ECM and the functions with the alternator system vary by manufacturer. So let's talk about the 12 volt charging system operation. During the engine cranking, the battery actually supplies all the electricity, and the alternator really isn't functioning during this point. When the engine starts running, the charging system then takes over. It takes a look at how discharged the battery is and is looking at the consumption that's needed by the vehicle to run the different accessories. The voltage regulator on there, or in some cases the ECM, keeps the alternator output at a preset charging voltage of this 13 to 15 volts. Different vehicles use the voltage regulator with a sensing wire. Some vehicles use the ECM with a different control strategy that has a pulse width modulated signal. The charging voltage is higher than the battery voltage, so current flows back into the battery, and it does more so when the car has been recently started because it's discharged, and as the battery starts to fill, it'll pull back on the amount of current that's being fed to the battery. Inside the alternator, there's really two main parts. There's what they call a rotor, and that's located in the center of the alternator housing, and that creates this rotating magnetic field that induces voltage. It induces that voltage through what's called a stator, and that's a stationary set of windings that surround the rotor. The rotor literally spins inside of these set of windings. This is what generates electricity when the rotor field windings are spinning. So as that rotor spins faster, it actually generates more electricity. Here we can see an illustration. You can see that the rotor piece spins in the middle between these two outer windings. And this induces a voltage that wants to turn. And it doesn't matter which way it spins necessarily, it will cause current to flow in one direction or the other, depending on the direction that it is being turned. In order to use this system in a 12 volt DC electrical system from an alternator that produces AC electricity, we have to change that AC electricity into DC. That's called rectification or rectified. And in order to do this, we use some diodes that allows current to flow in only one direction. Typically, most alternators will come with what they call 6 diodes that control this flow. And it takes the above and below line of the voltages that we would see in our AC systems, typically similar to how our houses work, and changes it into a DC signal. It's a great system that produces smooth DC electricity as long as the diodes are operating correctly. When we look at the internal parts of an alternator, you can see a breakout of the main parts that are typically found inside an alternator. There's a rotor assembly that we've already mentioned. There's what they call brushes that actually allow electrical current to be carried to something called slip rings. And that's what fields that rotor to create that field. And then we have a rectifier assembly that we just talked about for cleaning up the AC electricity. On the outside of the housing is the stator assembly, and the rotor spins inside this. Then we have the alternator housing, that's the metal component that holds all these parts together. And then on the front, there's usually a fan and a pulley assembly that can be changed depending on the vehicle needs. Bigger pulleys and smaller pulleys and different variations of fans can be put on an alternator. And then the last component is usually the voltage regulator, and that's what holds our voltage where it's supposed to be, between that 13 to 15 volts. The alternator rotor assembly is extremely dependent on having some bearings in there where it spins. So the rotor assembly consists of some field windings that are mounted on a shaft. This is how we create a magnetic field. And then the alternator bearings produce a low friction surface for the rotor shaft so that it can spin freely. If you look closely, you can actually see where the alternator brushes make contact with the slip rings. And what happens here is as we induce a voltage into those windings in there, we create this very strong magnetic field. As mentioned previously, the alternator has these slip rings. They're mounted on the rotor shaft to provide a DC current to the field windings. Each slip ring is connected to one end of those windings. And this is used in collaboration with a set of alternator brushes, which have little springs on them that actually push them out against these slip rings. And that's what carries the voltage. And if you're asking yourself, do those brushes wear down? They certainly do over a long period of time. Those brush springs keep constant contact. And of course, even with having a very smooth surface, there is some wear that does occur. So the alternator has an alternator rectifier, or basically a diode assembly. These 6 diodes convert the stator current, which is AC voltage, to a direct current, DC current. The full wave rectification allows us to collect both the positive and negative polarities, but keep them both on the positive side. So it actually rectifies that unit and cleans up the signal to give us this bumpy looking pattern as voltage goes by, or as the magnetic field is being broken. The rectifier diodes are mounted in a diode frame, or what they call a heat sink. This heat sink usually is something that's designed to allow some of that fan air to blow over it to keep those diodes cooled down. The alternator stator has 3 sets of windings, and each set is wrapped around an iron core. The iron core is used to concentrate and strengthen the field around the windings. The stator produces electrical output. Stator windings connect to what's called the rectifier for that rectification of the electricity. The alternator housing is made up of the drive-in frame, these slip rings that are on the end frame, and then the end frame bolt. It literally is usually 2 or 3 pieces that separate. On the front end of the alternator, we would find the alternator fan, and mounted on the front of the rotor shaft itself. So that actual pulley is spinning the rotor inside that alternator. And then the alternator pulley usually is connected to some kind of belt that's driven by the motor itself. Here you can take note of what a cross section of the alternator might look like. You can see the diodes are on the back end, and then you can see the slip rings and the brush assembly that's connected to the rotor that runs all the way to the front pulley where the fan is. Now on the outside there in green are the stator cores and the actual stator windings noted in red. So today with the voltage regulator, most vehicles are using the ECM in place of what they call an alternator mounted voltage regulator. Originally, years ago, the voltage regulator was even separate from the alternator, and you could find it on the side of the engine bay somewheres. But today we use the ECM to actually control or dictate the amount of voltage that we want out. The ECM uses an electronic circuit to control the alternator output. It actually feeds it a signal. And this changes the amount of current flowing through the rotor's field windings. And that maintains a preset charging voltage that's programmed into the ECM in most cases. The ECM charging system on here monitors the power through the power control module, can change the charging system output, and it reacts to changing operating conditions. And because it's a computer, it can react very quickly. The computer controls what they call a duty cycle of the alternator's field. This duty cycle is a percentage of time that current is fed to the field windings. And on most vehicles, 50% duty cycle would be considered normal operation. Some of you may be familiar with the belts, but we'll go over them. They're powered by the crankshaft pulley, and they turn the alternator pulley and rotor. And there's three types of belts that are typically found on a vehicle. And keep in mind, there's other systems that can be turned by different belts or the same belt on the vehicle, such as your power steering and so forth. So originally we had V-belts. They're older. They were very popular. You still see them every now and then. Then we went to a cogged V-belt, which was supposed to help with noise. And the most common that we see today is what they call the ribbed belt, or sometimes referred to as a serpentine belt. The next area we need to become familiar with are the charge indicators that are found on a vehicle. Every vehicle has some kind of charge indicator. The alternator warning light is usually found on the instrument panel, and it glows only if the alternator output or the battery voltage is below a specified level. The next type of indicator that we see is called a voltmeter. It's usually in the instrument cluster display as well, and it indicates the voltage output of an alternator. So it'll usually have a number, it's 12, 13, 14, then it goes up to. And the other style is called an ammeter, and this is also located usually in the instrument cluster display. And that indicates the current output of the alternator, and it measures the current flow to and from the battery. So as you start the vehicle, you can literally see the needle move in the negative direction as the battery is being discharged and current flows in the opposite direction. Next, let's discuss some hybrid charging systems. So many hybrid vehicles don't have a conventional alternator, especially if they're an electric vehicle only. Some of the early hybrids, you may have seen some variations, but most of these hybrids today don't come with what they call a true alternator. Instead, they have what they call a motor generator. That motor generator is what recharges the high voltage battery and sometimes the conventional 12-volt battery. And it does this through the regenerative features of braking, regenerative braking that you may have heard of in the past. Major parts of a hybrid charging system include the motor generator, which uses that braking energy or engine power to produce electricity, sometimes called regenerative braking. The hybrid instrument panel display shows the battery state of charge, the power regeneration, and the power remaining. It's much more elaborate than what we're used to on an EV or hybrid system. The high voltage power control module converts the high voltage AC from the motor generator to the 13 to 14 volts DC. And you'll notice some similarities. It's high voltage, but we're still getting an AC signal out of this motor generator. And we still need to rectify it into some kind of 13 to 14 volts to be used by our conventional 12-volt systems that are still on the vehicle. So on a hybrid vehicle, we have a high voltage battery, and that provides the large amounts of stored electrical energy for the engine starting and vehicle propulsion down the road. In addition to this, we'll have some kind of hybrid control module that coordinates information that's between the high voltage power control module and the other engine control modules that are on the vehicle to determine where we need certain amounts of power. Remember, there's high voltage systems that are on a high voltage vehicle or a hybrid vehicle, and there are low voltage or 12 volt systems that are still there. And we need energy for both of these systems that needs to be rectified into usable energy for those low voltage 12 volt systems. The internal combustion engine on here is another consideration we need to talk about. So when the hybrid has been driven the maximum range on electrical power that the battery has, it needs to start the internal combustion engine to do a couple of things. It may use it to partially recharge the battery, it may use it to propel the vehicle, and it can obviously use this to supply that 12 volts for the vehicle and the system. On many hybrid vehicles, there's actually kind of a balance between the engine and the electrical system working together in unison to give them those high mileage per gallon ratings that they often get. The high voltage power control module on these systems usually has something that harnesses energy from the energy powered motor generator. It routes energy first and foremost typically to the high voltage battery. It rectifies the AC coming out of the motor generator and outputs a smooth DC through these orange power cables to the high voltage battery. Whenever you see orange, remember these are high voltage and very dangerous. We don't want to be just grabbing a hold of these wires unless we know what we're doing. But we're stepping down the high voltage for the interior basic systems for the car electrical system. Another interesting part about these, what they call mild hybrids, is the stop-start system that's in them. And that can shut off the internal combustion engine when the vehicle comes to a stop with the engine idling. It uses the high voltage starter alternator to restart the engine. So it uses the high voltage battery to rotate this motor generator to start the engine back up. And a lot of these hybrids don't even have starters. They literally use the motor generator to start the engine. It can also be used to recharge the vehicle's high voltage battery, and in some cases it'll help propel the vehicle down the road. These are on mild hybrids, so you might see a car that has like a 20% boost power. Almost acts like a turbocharger. When it's going down the road, the electrical motor generator can hop in and help accelerate the vehicle down the road. All right, and that's a general overview of what the hybrid and the charging systems look like. Remember, when we get into some of the electrical courses later on, we get much more specific into what's going on with these components inside of them. It's important, though, in this early stages of your classwork that you get a general idea of what these systems do and what their functions are. Again, if you have any questions, feel free to email me, send me some kind of message, and we'll coordinate a time that I can further explain any areas that may still be unclear to you. Thank you for watching again.